Darshan, Fahad, Madiha, Priya, Rafat, Sahal, Samia, Wafia. Alright, so see, we have completed still chapter number 5th. Now, chapter 6th we'll start. We'll actually now start with your unit 4. Unit 4 is all about EMI and AC. It's a short unit. Especially EMI. EMI is a very, very short lesson and a very easy lesson to score. Even AC is a short lesson, but AC can be at times a little tougher or a little more difficult than EMI because of certain factors that we'll study. But even that time, I'll tell you if you remember a few things, then AC is also a very easy chapter. From here, electromagnetic, EMI is your electromagnetic induction. Electromagnetic no, Darshan, I was talking about EMI and AC. AC is a little tougher than EMI, but EMI is a very short and very easy lesson to score. Yes, Fahad. Fourth chapter, not just fourth chapter, till fourth chapter. First four chapters are quite tough, and they are the basics for your electromagnetism. See, you must have noticed now in now from EMI, AC, you won't be having very much new concepts. Like I'll be starting with magnetic flux. Magnetic flux will be just what you've studied, electric flux. Right, so yes, till chapter 4, please make your base strong. Wherever you are having doubts, please ask me. Chapter 5th is also very easy. That chapter we have completed just. I think earth magnetism also we have done. Class, one more thing. Earth magnetism we have done because that can come in your entrance and that is essential for your knowledge. That's why we did it in brief. Earth magnetism will not come in your board exams. Nobody is going to ask you topics from earth magnetism. Gauss law in magnetism can be asked. Just mark it or write it somewhere so that whenever you are revising, you're not wasting time on revising earth magnetism. Electromagnetic induction is chapter number 6 from your NCERT. And AC is alternating current. This is chapter number 7 from the NCERT. So these two chapters are very scoring and they are based on electrostatics plus magnetostatics. So now you just have to combine and relate those. We'll start with electromagnetic induction. Now from your first book, you have all the short lessons only. In your first book, whenever you are revising, no class, first 4 lessons are lengthier, they are tougher, and they are the basics for your core chapters, you can say, for the whole book. While the other 4, EM waves, EMI, AC, magnetism, and matter, these 4, these are to improve your score. Yes, theory part comes and numerical part can come. That table we remember, we did it. Comparison between electrostatics and magnetostatics. There we had seen certain formula there. From there, simple numericals can come the way we have done. Otherwise, theory questions will definitely come from this. What you have written, diamagnetic, paramagnetic, from that table. Now, for electromagnetic induction. Now see, the need to be starting with electromagnetic induction, or we had to start with electromagnetic induction, was the fact that see, if you had a current carrying conductor, fine, a current plus a conductor is the current carrying conductor, it produced a magnetic field. This is what we have seen till now. Current carrying conductor is producing magnetic field. Current carrying conductor is producing magnetic field. This we were continuously studying. Question then arises, will magnetic field plus the conductor produce current back or not? Can this be possible ever? This is possible. We have seen the formula also. We have seen the methods also. We have seen at a particular point we have to calculate the magnetic field due to current carrying wire. How will we calculate? This we have seen. But if we reverse this, will current be produced? So certain experiments were done by Faraday that we'll see in the next class. Answer came out to be yes, definitely this is possible, and that's why we had this phenomenon of electromagnetic induction. Everything here is based on induction. uh, Induction is there in your syllabus. So induction, when we'll do induction this time, it will become more clear why is the name of the chapter as electromagnetic induction. By the name, I think you must be able to figure out just the fact that it's based on electromagnetism. Rest of the things, this induction part is very important, and half of the chapter is induction. That we will see later. Now, starting with magnetic flux, obviously today is a very short theory class for us because then you have your test. Magnetic flux is, see, if I have, suppose, this is a sheet that I have. Now from here, one magnetic line passed through, another magnetic field line passed, another magnetic field line passed, another magnetic field line. These are all magnetic field lines. And at this surface, so they are making angle of 90 degree. Fine. Now, how many field lines are passing? 1, 2, 3, 4. 4 magnetic field lines are passing and they are perpendicular also. So we say magnetic flux of this will becomes 4. So what is magnetic flux now? It's the number of field lines that are crossing an area normally perpendicularly, or you can say making an angle of 90 degree. This means the same. So number of magnetic field lines crossing area normally is magnetic flux. In case of electrostatics, we had seen electric flux was what? Electric flux was number of electric field lines crossing area normally. Here we have number of magnetic field lines crossing area normally. Now the formula for it. See, formula is very predictable and formula is very easy. It's a scalar quantity. SI unit is Tesla meter square. How is the SI unit? I'll show you. See, for example, this is a sheet that I have. This is the magnetic field. I have to take the perpendicular to it. I have to drop a perpendicular because I have told you class in when we were discussing electric flux also, that time also we had seen we have to choose area vector. Area vector is just perpendicular to this. This is area vector perpendicular to the base. And the angle between the magnetic field and the area vector, this is known as theta. So never choose angle between the plane or the magnetic field. Never write theta this. This is not theta. Theta is always the angle between the magnetic field and the area vector. Fine class, this is theta, angle between the area vector. And what is area vector? Whichever sheet you have, you just have to drop a perpendicular to it. That gives you area vector. Right? So area vector, choosing area vector is nothing. You just have to draw perpendicular to it. And wherever is the magnetic field line, that angle with the area vector becomes theta. If it's overlapping, then you say 0 degree. If it's anti-parallel, you say 180 degree, whatever you have studied. And also magnetic flux is what? This is B dot S. That is Bs cos theta. And theta I have defined. S is what? S is the surface area of the sheet. P is the magnetic field. N cap is the area vector, and theta is the angle between them. Fine. So it's very much similar and exact replica of electric flux only. It's a revision also, kind of revision for electric flux as well. And this is a new topic also. So note it down till here. Then we'll do numericals on this.
Ma'am, can you scroll down?
Done? Just let me know when you've written. Others have also done. See, let's start with a question. I think 2 questions I'll discuss, then I'll stop. So you can appear for your test. See, this question says what? It says magnetic field of 2 Tesla exists in space. It is inclined at 30 degrees with the plane. It means this is the plane and this is the magnetic field. Angle between the magnetic field and the plane. This angle is given as 30 degrees. You have to find out the magnetic flux as the surface area is 10 meters square. Magnetic field is 2 Tesla. Theta. C class, what angle should I choose? So 30 degrees? 1/2. No, angle's value. You are telling the complete value, no? What 30 degree should I write? Others also. Free class. Drop your perpendicular n cap first, no? N vector, area vector. Yes, right. This angle you have to choose. This is 60 degree. So theta will be 60 degree for you, not this angle. This is the angle that the plane and the magnetic field are making. This is 60 degree what is required. Now you can easily calculate magnetic flux. This is magnetic B dot S. So PS cos 60 degree, which will be 2 into 10 into, now you can say 10, and that will be 10. Webers is also the unit of it. One more thing, class. Weber is also the unit of it, or you can write Tesla meter square. Quickly copy this question. One more question we'll discuss. (60° by this method. See, if area vector is perpendicular, it means this complete angle is 90 degrees. From here, 30 degrees given. What will be left? 90 degree minus 30 degree, that will be 60. Like this. Written class.
Yes, ma'am.
Others also, apart from power.
Ma'am, this 30-degree angle will be given, right?
Any angle will be given. Any angle can be given if this 30 degree is given. 30 degree in the sense angle between the plane and the magnetic field is given. Then you will not consider that. You will subtract it from 90 degree and get it whatever is the value. Otherwise, it can happen that the angle between the area vector and magnetic field is directly given. It can be framed in the question, no, that the angle between the perpendicular to the plane of magnetic field and the magnetic field is this much. So it means you directly have your theta, whether it's 30, 90, not 90, whatever is the value. Fine. Here what happened, it was given as the angle between the plane. So any angle can be given to you if it's angle other than this theta, that is between the area vector and the magnetic field. Then you have to somehow find it, because theta is that only. Got it, Sahil?
Got it, ma'am.
One more question, let's do, yes. since Cartesian plane form, Cartesian. Magnetic field is given. Magnetic field is 10 I cap. See here, no. Solving vectors is very easy. Just one thing you have to write. If you write that thing, you will be able to solve the whole question completely. Magnetic field is what? 10 I cap plus 3 J cap plus K cap Tesla. Exists in space. You have to find out the flux through an area 2 meters square in YZ plane. So what will be the unit vector that I should write along with area? Can anyone answer this? It's given in the YZ plane. So
J cap.
yes, Fahad, J cap. Okay. Anyone else? All of you agree with him? Or a different answer somebody has? This is Y axis. Here your sheet or whatever is the plane that has been kept like this in YZ plane. Now what will be the area vector? Where will the area vector go? K cap. Madhya says K cap. Anyone else? Area
K cap.
vector. K cap. See, XY plane is there. This you have understood. It's kept in XY plane. Y here. Z. Don't go by the drawing because it's not that symmetrical. It is kept in XY plane. Now area vector, what do we write the area vector or how do we write the area vector? Area vector is written by the perpendicular. That's what we have studied. Whatever is your plane, area is always chosen as the perpendicular. So if you drop a perpendicular, where will the area vector point? That is your x-axis, no class. So y-axis has j cap, z-axis has k cap. Area vector will be given by I cap. Tabhi to it's perpendicular to the YZ plane. Got it? Yes. So I cap will be there. This will be 2 I cap. Now this is sufficient to prove, this information is sufficient to prove the fact that this is lying in XYZ plane. That's why you have I cap over here. Had it been XY plane, you would then have written K cap. Had it been ZX plane, then you would have written J cap. Just perpendicular to it. Area vector, remember class, is always perpendicular. Now you can resolve this. So 5 will be what? B dot A. B dot A simply multiply 10 I cap plus 3 J cap plus K cap dot what? 2 I cap. So magnetic flux will be equal to, this is, you're just multiplying. So this gives 20. I cap dot I cap will be 1. All these terms get multiplied by 0 because nothing is here. So 20 Weber. Got it like this if it is in Cartesian form. Above one, previous one was in polar form. Note down this and please text me when you're done writing part. Yes, you can write Tesla meter square as well. 1 Tesla meter square is actually 1 Weber. So that's why you can write Weber as well. Weber is also there, or you can write Tesla meter square. That is also there. All of you have done. All of you have done. Except for, I think, only Priyadarshini, Fahad, and Samya have texted me. Okay, class. Fine. Magnetic flux. Now we'll start with Faraday's experiment from the next class. Magnetic flux was a small topic and it was the first topic of this. Now, please be ready with your answer sheets. We'll start. First one is not exactly a derivation. You can say derivation for a square. Square, we have not done it separately. So as a question also you can do. It's not a derivation. Derivation because side is specifically given. 2a side is given. So you can normally solve this in the form of a question only. And regarding Abia and Priyadarshini. Okay, fine then. Avi, you were also not aware. Priya, I remember you haven't done these topics because you had changed the batch. Okay, Abhi. You were not aware about the test. Fine. Okay, then you can leave, both of you. Darshan, you were there in the last classes. All the classes you had attended, Darshan. Then what happened? How come you didn't know about the test? Others you were aware, no? I had announced the test or not? Fahad and other, Madiha, you all were there now in the class. Did I announce the test or not?
Yes, ma'am, you have said.
The complete chapter, no? Okay, Darshan, then you can also leave if you were not aware about the test, but please stay alert in the class whenever you are attending the class because these announcements are made on the class only. So take the screenshot after you revise this lesson, then send me it as an assignment.
Ma'am, what is M here in the third question? 20 M Tesla, right?
Which question?
Third question, ma'am. Micro Tesla, right?
Yes, no, that's not micro Tesla. That's milli Tesla. Micro has a
No.
symbol like U.
Okay, so milli.
Yes,
So what
20
is the power?
Tesla. So you have to convert it into the SI unit, that is Tesla.
Okay.
No, for the second question, see, two cases we had done for circle. One was at the center of a circle where we had derived of the formula for circle, and one more we did at the axis. If at the axis of the circle a magnetic field is produced, where we kept the circle in YZ plane. That derivation you have to do, not toroid. Okay, Wafia, you can leave then. Okay, Madhya, you can leave. Samya, you can also leave. I have a seat.